Close your eyes and try to picture a kind of loneliness the human mind almost refuses to simulate. Not the loneliness of being far from home, but the loneliness of being inside a universe that appears to have no home at all. Imagine you are suspended inside a supervoid, and darkness is not a mood but a measurement. The sky is not empty because you are blind. It is empty because, in every direction, there is almost nothing to be seen. No familiar scatter of stars, no faint galactic haze, no Milky Band to reassure you that structure exists beyond your own small neighborhood. If your civilization is young, if your instruments are crude, you might conclude that the cosmos is a sealed room and that you are alone inside it. That thought is not just frightening, it is quietly corrosive, because it does something science has spent centuries undoing. It places you back at the center of a story you cannot verify. The Botez void is often nicknamed the Great Nothing, and the nickname lands because the scale is so hard to hold in your head without it slipping into metaphor. It is roughly spherical, about 330 million light-years across by many descriptions, and it contains only a few dozen known galaxies, where thousands might be expected in a comparable volume, a dramatic underdensity that feels less like a statistical fluctuation and more like a missing chapter torn from the cosmic record. It was identified in redshift surveys in the early 1980s, not because someone saw a hole in the sky, but because careful mapping revealed that the usual crowd of galaxies simply was not there. And then comes the truly unsettling implication, one that astronomer Greg Aldering has been quoted expressing in plain language. If the Milky Way had been sitting near the center of such a void, the broader universe of galaxies might have remained hidden from us until astonishingly late in our technological history, because there would have been so little nearby evidence to force the idea upon us. The Botez void is not just emptiness, it is a lesson about how contingent obvious reality can be, depending on where you stand. Voids are not supposed to feel like rule breakers, because the standard picture of cosmic structure, shaped by inflation, dark matter, and the slow pull of gravity, naturally generates a foam of filaments, walls, clusters, and the spacious cavities between them. In that framework, emptiness is not an exception, it is part of the design. What unsettles us is when emptiness appears organized on a scale that seems to strain the time available for structure to form, because the universe is old but not infinitely old, and growth has a speed limit set by causality, expansion, and the way gravity competes with that expansion. When a void looks too large, the mind reaches for dramatic explanations. But the sober scientific response is usually more interesting. It asks whether we are seeing one coherent thing, or whether we are stitching together multiple adjacent voids into one psychological object, because our pattern-hungry brains dislike messy boundaries. Even inside the Great Nothing, the few galaxies we do see may trace shapes that hint at larger architecture, remnants of walls, filaments, or the frayed edges of neighboring emptiness, suggesting not a cosmic tier, but a cosmic geometry we are still learning to read. Yet, the Botez void is only the warm-up, because it is darkness by scarcity, not darkness by physics. If you want a universe that is genuinely dark, you have to move backward, farther than any local structure, to a time when there were no stars at all, no galaxies, no planets, no visible beacons of any kind. The cosmic dark ages are not poetic branding. They describe an era when the universe, in the wavelengths human eyes evolved to use, offered essentially nothing. After the Big Bang cooled enough for atoms to form, the cosmos entered a long stretch where the raw ingredients of light existed: hydrogen, helium, dark matter, scaffolding. But the engines that turn matter into starlight had not yet ignited. For hundreds of millions of years, the universe was not empty. It was simply unlit in the way we instinctively define light. To understand why that darkness lasted, you have to accept an idea that feels backward at first. The early universe was not dark because it lacked energy. It was dark because it had too much of the wrong kind of interaction. In the earliest times, radiation dominated. Photons battered matter so constantly that stable atoms could not persist. The universe behaved like a hot, dense plasma, where light could not travel freely because it was always being scattered. Then, as expansion diluted everything, a transition occurred. Matter took over as radiation redshifted and thinned, and recombination allowed electrons to settle onto nuclei, creating neutral atoms and finally giving photons longer, cleaner paths. In principle, that sounds like the moment the lights should come on, but what came on was not a starry sky. It was a uniform glow, a black-body haze that would have looked warm, then redder, then eventually slid out of visible wavelengths altogether as expansion continued. Darkness fell not because energy vanished, but because the universe's background ember cooled into infrared and microwaves, leaving our eyes with nothing to catch. And in that new darkness, another actor mattered more than any visible glow: dark matter. We infer it because galaxies rotate too fast for the mass we can see, and because large-scale structure forms in patterns that ordinary matter alone cannot easily explain. Dark matter does not shine, it does not absorb light, it barely acknowledges the electromagnetic world, and that makes it both elusive and foundational. In the Dark Ages, dark matter did what it is best at doing. It quietly deepened gravitational wells, forming a hidden web of filaments and halos. Normal gas, mostly hydrogen, drifted into those wells, not dramatically, not like water into a drain, but gradually, accumulating density and losing energy through mechanisms dark matter does not have access to. This difference is crucial. Normal matter can radiate away heat. It can cool. It can collapse further. It can cross thresholds that allow fusion to begin. Dark matter cannot do that, so it becomes the architecture rather than the fire, the frame rather than the flame. For a long time, our story of the early universe was limited by the kind of eyes we built. Optical telescopes gave us galaxies, but only after galaxies existed. Then Hubble, almost as a dare, stared at a patch of sky that looked like nothing, and the deep field taught us an enduring humility. The universe is not obliged to reveal itself at a glance. With long exposure and exquisite sensitivity, empty sky became crowded, and distance became time, because the farther you look, the older the light you catch. The technique of reading spectra, of measuring redshift, turns that light into a timeline, letting us separate what only appears adjacent in a two-dimensional image. By that logic, newer instruments like the James Webb Space Telescope extend the frontier because infrared can collect photons that have been stretched by expansion beyond the visible, pushing us closer to the era when the first galaxies were assembling. But there remains a wall we cannot simply outspend with bigger mirrors. There is a point where even Webb's vision fades, because before the first luminous objects, there is no starlight to gather. That is where the strangest idea becomes the most practical one. If the earliest universe is invisible in the optical, then stop using optical language to ask the question. Hydrogen has a whisper, a radio signature at 21 centimeters associated with a hyperfine transition, and when you redshift that signal across cosmic time, it becomes a long wavelength breadcrumb trail through the Dark Ages and into the epoch of reionization. Experiments like EDGES were designed to detect that global signal, not a picture of individual galaxies, but a faint, sky-averaged imprint that would tell us when the first stars began to alter their environment. In 2018, EDGES reported a surprisingly deep absorption feature, often discussed as a potential window onto cosmic dawn, and it triggered exactly the kind of scientific drama you want, not because drama is entertaining, but because it is what happens when data threatens to outgrow the models we rely on. If the signal were real as originally interpreted, it would have implied either unusually cold hydrogen, an unexpected radio background, or more exotic physics, the kind of result that forces the field to either sharpen its instruments or revise its assumptions. But the universe does not hand out revelations without demanding receipts. Follow-up efforts have repeatedly emphasized how brutally difficult these measurements are, because the desired signal is buried beneath bright foreground radio emission from our own galaxy. and beneath the fingerprints of instruments themselves. In 2022, CERES-3 reported a non-detection that challenged the EDGE's claim, arguing that it found no evidence for the specific feature and that the earlier result was not supported by their data, a reminder that in frontier science, the line between discovery and systematic error is thin enough to cut you. This is the part of the scientific process I personally find most bracing, not the initial announcement, but the long, quiet season afterward, when the community tries to reproduce a whisper, and the whisper keeps changing shape depending on who is listening, with what antenna, under what sky, with what calibration. Philosophy. The right emotional posture here is not cynicism, it is patience, because patience is what reality demands when it speaks softly. The next chapter is being built in places that look, at first glance, like the opposite of cosmic grandeur, wide emptiness on Earth, far from cities, far from transmitters, far from the constant electronic conversation our species cannot stop having. Arrays in Western Australia, including the growing SKA-Low project, are designed to bring statistical weight and sensitivity to the 21-centimeter hunt, scaling up from Pathfinder instruments toward an observatory with, on the order of 131,072 antennas, arranged in stations across a vast radio-quiet landscape. Even early deployments have begun producing first images that hint at what this kind of instrument can become, not because it is pretty, but because it is disciplined, because it is built to measure what is almost immeasurable. And beyond Earth, the logic becomes almost inevitable. If our planet is too loud, then the far side of the moon, shielded from much of Earth's radio noise, starts to look less like science fiction and more like the next quiet room we will inevitably seek. If we succeed, we will not see the dark ages the way we see a galaxy. We will reconstruct it the way you reconstruct a landscape in fog, from gradients, from absences, from the subtle ways hydrogen changes its behavior when the first light sources begin to heat, ionize, and reshape the cosmic medium. That is a different kind of intimacy with the universe, not the intimacy of a photograph, but the intimacy of inference. The kind that asks you to trust careful thinking when your eyes cannot be trusted. If there is a soft invitation in all of this, it is to let the universe retrain your intuition, to notice how often nothing is just something you have not yet learned to detect, and how often the most important structures are built in silence long before they announce themselves in light. The darkest eras were never empty. They were only waiting for a way to be heard.